Bit of a different video today. We're going to discuss a couple of examples to help solidify some of the concepts of complex numbers. So over here we got a sheet of 8 questions, and we're going to work through them together. Question 1. Given the complex numbers z equal to 3 plus 2i and w equal to 4 minus I, evaluate 3z minus w and the product w times z. So for part A, we got 3z minus w. Well, handling the real parts and imaginary parts together. For the product of w times z, well, w was 4 minus I and z was 3 plus 2i. But we know that I squared is minus 1. Okay, this is done with question 1. For 2, write 1 plus root 3i over 1 plus I in the x plus yi form where x and y are real numbers. Well, because we never want to express a complex number with the denominator of a complex number, we need to kind of realize the denominator by multiplying by the conjugate. Doing all the necessary multiplication out. Grouping all the reals and imaginaries together. So, at least we got x to be 1 plus root 3 and y to be root 3 minus 1 all over 2. Now for part B, by expressing the numerator 1 plus root 3i and the denominator 1 plus I in trigonometric form, show that that complex number is equivalent to root 2 cosine pi on 12 plus I sine pi on 12. Simply for the magnitudes alone of the complex numbers, we know that the radius is going to be 2, and the argument, which is the arctangent of root 3 on 1, is going to be, and for the denominator, its radius is going to be root 2 by Pythagoras theorem again, and its argument, I'm going to use a different letter so that you avoid confusion, is going to be arctangent of 1 on 1, which is going to be pi on 4. Okay, so converting this entire complex number but this is a division of complex numbers. And what have we learned about division? The moduli divide and the angles subtract. So what is 2 divided by root 2? And since their moduli subtract, using your answers in part A and part B, find the exact values of sine pi on 12. Well, we know that in the Cartesian equation form of the complex number can be decompose down to 1 plus root 3 all over 2, root 3 minus 1 all over 2. But because now we want the value of sine pi on 12, all we need to do is just equate the imaginary components to the imaginary components. So the imaginary component in Cartesian form was root 3 minus 1 all over 2. And the imaginary form in trigonometric form, the imaginary component in trigonometric form is root 2 sine pi on 12. And we need to find sine pi on 12. By rationalizing the denominator, we see that and we're done number 2. For number 3, if the polynomial in terms of z is z4 minus 2z cubed plus 14z squared minus 18z plus 45, show that z minus 3i is a factor of the polynomial and solve the equation p of z is equal to 0. As we need to show that z minus 3i is a factor, then that means z equal to 3i is a root. If z equal to 3i is a root, that means if we take 3i and put it into all the z's in this complex polynomial, then it means we should get 0. And there we go. We've shown that z minus 3i is indeed a factor of this polynomial. For part B, where we need to solve the polynomial, we know from the conjugate root theorem that the complex conjugates must always occur in conjugate. The complex roots will always occur in conjugate pairs for any polynomial with all real coefficients. In this case, 1, minus 2, 14, minus 18, and 45 are all real coefficients. So if z minus 3i is a factor, so is z plus 3i. Multiplying the two factors together, we have obtained a quadratic factor of this quartic equation. Because the original polynomial is indeed a quartic equation, it must be able to be decomposed into a quadratic factor and another quadratic factor. But here's the thing, we don't know what the second quadratic factor is. As we don't know what the second quadratic factor is, let's just say that it is some quadratic called az squared plus bz plus c. Now, we need to expand this out and slowly equate coefficients. Expanding the right hand side out. Immediately we see that 9c must be 45, which indicates that c itself must be 5. We see that 9b must be minus 18, which indicates that b must be minus 2. And we see that az to the power 4 must be equal to z to the power 4, which again means that a must be 1. Giving our attention to this second quadratic factor, this second quadratic factor must indeed be 0 because we want to solve for the original quadratic to be 0. Putting this in the quadratic formula, so we got 2 roots from this quadratic factor. Therefore, all 4 roots of the original quadratic are going to be and we do expect 4 roots because this is a polynomial of degree 4. And with that, we're done with question 3. For question 4, do complex numbers u and v satisfy the equation of u minus v equal to 2i and uv equal to 10? Solve for u and v, leaving a solution in Cartesian form, where x and y are themselves real numbers. Now, over here we got 2 equations with 2 unknowns. So this is indeed a simultaneous equation sort of thing going on. Let's call these equation 1 and 2 respectively. From equation 1, taking equation 1 and substituting it into equation 2. Over here we have some sort of a quadratic equation in terms of v, where the coefficient is 1, the coefficient is 2i, the coefficient is minus 10. So because this is a polynomial of not all real coefficients, we do expect 2 roots, but they will not occur in conjugate pairs. Solving this, so over here we see that v is equal to, which indicates that u is going to be and with that, we're done question 4. Question 5 states that for the complex equation minus pi and 4 less than or equal to argz less than or equal to 2 pi and 3, sketch the locus of points z satisfying the equation. And since that was part A, let's see what part B is. Determine the Cartesian equations and inequalities. Okay. So on the Argand diagram, is the argument must be greater than or equal to pi on 4. So just somewhere here. But it goes on forever. And as it must be less than or equal to 2 pi on 3. Again, somewhere here. And since the argument must be within these bounds and also including the boundaries of these bounds. Sorry, I just realized it must be within these bounds, but it also must include the boundaries of these same bounds. So it must be anywhere between here. Now for part B, determine the Cartesian equations and inequalities. Well, since this point is pi, since this arrow is pi and 4 inclination from the real axis, this line must simply be y equal to x. And because this line also passes the origin, and this ray has an inclination of 2 pi and 3 from the real axis, this guy must be 2 pi on 3 times x. That being said, what is the intersection of these two loci? It's going to be, because anything above this line and intersecting, and what is tangent of 2 pi and 3? These are the two inequalities in Cartesian form. And with that, we've done number 5. For number 6, the set of points in the complex plane which satisfies z minus 3 minus I equal to z minus a minus bi, where a and b are real constants, can be defined in Cartesian form as y equal to minus 2x plus 17. Determine the values of a and b, or find the values of a and b. We firstly need to make everything into a more standard form. Once again, what they're trying to say is that the distance, the z is from the fixed complex number of 3 plus I is equal to the distance the z is from the fixed complex number a plus bi. Now, to actually get the Cartesian form out of this, because z is equal to x plus iy, and because we can exploit this using this guy. Expanding everything out and simplifying it. Simplifying all of this. Trying to put all the y's to the left hand side and everything else to the right hand side. Making it to the y equal mx plus b form. Now, from this condition, we know that the coefficient of x must be minus 2 and the y-intercept must be 17. That being said, all of this must be minus 2 and all of this must be 17. Solving for a equal to something else. Solving for 17 equal to everything else. By putting this a which is 2b plus 1 into that a, we're gonna get now taking all of this and solving for b, we're gonna get 17 equal to half times 5b minus plus 9. And if we were to solve for b in this equation, And we will take b equal to 5 and put it back into that equation. And we've also finished question 6. Question 7. Consider the following set of complex numbers s equal to a set where z is such that magnitude of z plus 4 minus 5i is equal to 3. So this is a circle centered at minus 4 and 5 with a radius of 3. So sketch the set of complex numbers s in the Argand diagram. So this is a circle centered at minus 4, 5 with a radius of 3. Let's try our very best to draw this to somewhat to scale. Okay, all my markings are all half an inch apart from each other. So the center is somewhere here. With a radius of 3. Oops. Alright. So sketch the complex numbers of that set, which is once again a circle centered at minus 4, 5 with a radius of 3. That's it right there. Now for part B, determine the maximum and minimum values of absolute value of z. So what is absolute value of z? It is true that that is just the modulus of z. But when we write absolute value of z, what we equivalently mean is z. So how far z is from the origin. So in this case, from the origin. The maximum value would be, remember, all the z's that we care about lie within this circle, which is only a subset of the entire complex plane. So the maximum value of the modulus of z is starting from the origin all the way through the center of the circle and all the way to the circumference of the circle. Firstly, if we only consider this triangle here, where the hypotenuse is only from the origin to the center of the circle. How do we get the hypotenuse? Simply from Pythagoras' theorem, we see that this hypotenuse is going to be But we're not done yet because we still have this radius to add on. We still have this radius to add on to this line segment, which only went from the origin to the center of the circle. So we still need to add the radius of 3. So by Pythagoras' theorem, and that is the maximum value of magnitude of z. For the minimum value of z, because the maximum value of z goes all the way from the origin to the center of the circle plus the radius of 3, the minimum value of z is only going to be from the origin to simply just touching the circumference of the circle. So for the minimum value of z, of magnitude of z, it is going to be root 41 all the way to the center of the circle minus away the radius of the circle. So always use the center of the circle as some sort of an anchor point for all calculations. For part C, determine the maximum and minimum values of arg z. Now remember, the argument of a complex number is what the angle the complex number makes with respect to the real axis. So we use different colored pens to determine the minimum angle . This purple line is going to be the minimum. And this orange line is going to determine the maximum. Solely from the picture, if we were to label this angle from the imaginary axis to the purple line to be phi, and we label the angle from the purple line to the red line to be theta, and we also label the red line to the orange line as theta. These two thetas must be the same because this purple line and the orange line are both tangential to the circle, and because they are tangential to the circle, these lines must be perpendicular to the radius. Once again, therefore, the minimum argument of z is immediately going to be some sort of pi on 2 plus this phi. But firstly, going back to this picture, this theta here is surely an opposite over a hypotenuse, and the opposite is only the radius of the circle 3, and the hypotenuse of this red triangle, well, the triangles made up from this purple solid line, the radius, and the red line, is going to be root 41. But we also know based on the diagram, that the tangent of theta and phi is going to be the tangent of theta and phi is going to be this entire line drawn in pencil. Not sure how clearly you can see it, over this entire base. And although my drawing is not to scale, it's going to be 4 and 5. The height of this pencil drawing is going to be as much as this 4 in length of how much the circle has been shifted. And this adjacent of this triangle is going to be how much vertically this circle has been shifted. But what was theta? Theta was arc sine of 3 on root 41, right? And if you were to put this all, it's going to be approximately 1.76 radians. For the next part of the maximum possible argument, again back to our picture. If already theta phi plus theta gives us 1.76, the maximum argument is just plus another theta. And with that, we're done with question 7. For question 8, show that for every positive integer n, 1 plus I to the power n plus 1 minus I to the power n is equal to 2 to the power n on 2 plus 1 cosine n pi all over 4. Solve algebra really. For 1 plus I, in the cosine I sine form, by Demo's theorem, because we can put all the powers into the trig arguments, and also we can factor out the root 2's to the power n's. But sine is an odd function and cosine is an even function. And because we got positive I sine and negative I sine, and because we got a cosine and a cosine, factor out the 2. And with that, we're done with question 8 as well.